Good morning. Today we are doing Statistics and Probability 7.SP.7. These are simulations, which means we're pretending like they happen to figure out the possibility or the probability likelihood that it may or may not happen. So a softball pitcher averages 2 strikeouts after 6 batters. Okay, so first we need to figure out what her average or what her probability of getting a strikeout is. And so we put 2 strikeouts over 6 batters. I'm going to reduce that to 1 out of 3, okay? So that means 1 out of 3, one time out of every 3 batters, she will get them as a strikeout. So since she is facing 30 batters, you're doing one third of the time she's going to have a strikeout. So she will strike out 10 batters. I can't write. These are application problems. All right, number 2 is a little different, so I'm going to try to explain it the best I can. Camden does not like to pair his socks, so he throws them all in a drawer. He has 3 pairs of brown socks, which means he has a total of 6 brown. 3 pairs of navy socks, which means he has 6 navy socks. And 4 pairs of black socks, which means he has 8 pairs of black socks. So what that means is that he has a total of 6 plus 6 plus 8 socks total. Okay. On a dark morning, he pulls out 2 socks, and they want that probability to be a black pair. So we are going to, there are 8 socks that are black in the total number of socks, okay? So 8 slash however many total socks there are. Now, the reasoning that needs to make sense, and I'm going to write this so that you get it, is that total socks, not pairs, equals 6 plus 6 plus 8, which is 20. Okay? How do I do back? So the first pull is 8 out of 20. But the second time he pulls, there are only 7 black socks left, because if you drew the first one out, then there's only 7 left in that drawer. If you pulled 1 away from the 20, then you're only going to have 19 left. Okay, so this is pull 1, and this is pull 2 probability. So I'm hoping that makes sense, but that's how it works. If he had put the socks back in, then his probability would stay the same, but he needs 2 socks, so therefore he did it. So then you just multiply like fractions. 8 times 7 is 56. 20 times 19, I used my calculator, and I got 380, which, if you use your calculator to figure out percentages, is 14.7% of a black pair. Why is it more practical to simulate an experiment than it is to perform the experiment? Performing an experiment could take more time, could cost more. There's a lot of reasons, but just trying this, pretending like we did on number 2 and number 1, that is easier, often because it's faster and because there's not any randomness about it. It's this is what the probability should be, not always how it works out. Ollie, a 7th grade student, was at asked to flip a penny 100 times and record how many tails and how many heads came up. Before doing the experiment, Allie predicted that the probability of heads to tails should be 0.5, or 1 out of 2, or 50%. And that makes sense. There's only two options. It's just as likely to be heads as it is to be tails. But when the experiment was complete, Allie counted 77 tails and 13 heads. Were Allie's results consistent with her predictions? No. Because her results were 77% tails. The prediction was 50%. Her heads prediction, her heads results were 13%, but prediction was 50%. According to Allie's experiment results, predict how many heads Allie would get if she were to flip the penny 200 times. So here's what they're saying. Flip the penny 200 times. How many heads? So her original results were 13 out of 100. If we made it 200, so did it again, according to her results, it would be 26%, would be 26 heads. So basically, if that were true, then it would assume that she's going to just get 13 again out of that 100. What would you expect to happen to the results the more time Allie flips the penny? I would expect them to get closer and closer to 50, because we know that should happen. So that's one of the things about random and actually acting them out, is that is what, it doesn't always come out perfectly 50% or perfectly 25% or rolling a dice perfectly 1 out of 6. But if you kept doing it, that's why computers do the simulations now. It will eventually get to what the theoretical probability should be. The theoretical probability of flipping a coin should be 50% every time. But we all know that every time you flip a coin, it's not going to go heads, then tails, then heads, then tails. You're just going to have to keep flipping it until it ends up being at 50%.